Hello, in this session, let us discuss some of the concepts related to the DC generators. So, let us take the introduction part of DC generators. So, if you observe the definition which is given in the slide, an electrical machine which converts the mechanical energy into electrical energy is called as DC generator. So, any machine which converts a mechanical input such as mechanical force you can assume into an electrical output, that is the voltage or current, is called as DC generator. So before going to the concepts of DC generator, let us recall some of the basic concepts related to the electromagnetism or DC generators. First of all, let us take up magnetic field. If you observe the definition of magnetic field, the region or space around a magnet in which magnetic effects are felt is called as magnetic field. So here he is talking about the region or space or the area around a magnet. So if you consider this one as a magnet, a bar magnet, which is represented by a north and south pole, the region or space around a magnet, you can consider this is the area he is talking about. Area around a magnet in which magnetic effects are felt. Magnetic effects is nothing but magnetic force of attraction or magnetic force of repulsion. So that is called as magnetic field. If you observe the area around a magnet which is represented by magnetic lines of force, these are the magnetic lines of force. You can observe the red arrow mark what he has given. These are called as magnetic lines of force, which is called as magnetic flux. So he is talking about this area. The area which is represented by magnetic lines of force is called as magnetic field. So a magnet, any substance which attracts or repels the iron filings, is called as magnet, and magnetic lines of force is called as magnetic flux. You can observe the magnetic lines of force around a magnet, it is called as magnetic flux. And the other term is the magnetic force. What is magnetic force? The rate at which the magnet attracts or repels the iron filings. What is magnetic force? The rate of speed of attraction or repulsion. ಯಾವ ಸ್ಪೀಡ್ ಅಲ್ಲಿ ಐರನ್ ಮ್ಯಾಗ್ನೆಟ್ ಅಟ್ರಾಕ್ಟ್ ಮಾಡುತ್ತೆ, the rate of speed of attraction or repulsion, that is called as magnetic force. So you can observe this diagram. Here you can observe we have taken the magnetic field has been already, you can see the magnetic field which has been shown by imaginary lines of force. Actually the magnetic lines of force is called as imaginary lines which is not visible. Okay, the circle what you can observe, the red circle, you can assume as a iron which is placed in the magnetic field. Whenever the iron is placed in a magnetic field, it affects the magnetic effect. It feels the magnetic effect. You can observe the magnetic effect. That means it gets attracted or repulsed by a magnet. Okay. Whereas here you can observe which is placed in a non-magnetic field area. This is the area which is out of magnetic field. Okay. Here it does not exhibits any force of attraction or repulsion. Okay. So here you can analyze. This is the magnetic field area. This is non-magnetic field area. Okay. So here you can observe some of the properties of magnetic lines of force. The first property is the direction of magnetic lines of force is from north to south outside. If you observe the magnetic lines of force, it is from north to south. You can observe it is outside the magnet. He is talking about outside the magnet. This is the outside the magnet. You can observe north to south outside the magnet, and inside the magnet it is from south to north. If you observe inside the magnet, it is not shown. You can assume it completes its path like this. It starts, it moves towards the south. Inside the magnet, it comes like this. Okay, here you can observe it starts from north, moves to the south, around complete its path in the surrounding medium. Again, inside the magnet, if you observe, it comes and it completes its path. Like this, it will go. You can observe. So he's talking about these lines. The direction of magnetic lines of force, it is from north to south, that is north to south outside. If you come inside, it is from south to north. Okay. The second point is the magnetic lines of force always forms a closed loop. Always forms a closed loop. You can observe it starts from north, complete its path in the surrounding medium, again comes to the south, again inside the magnet. If you observe, it completes its path inside the magnetic field, inside the magnet like this. You can observe. First line, if you consider, it comes like this, again it completes its path. Second magnetic lines of force, if you observe, it comes like this, again it completes its path. Again third magnetic lines of force, if you observe, it starts from north, completes its path in the surrounding medium, comes near the south, inside the magnet it moves like this and completes its path. So this is regarding the second point. The third point is the magnetic lines of force follows the low reluctance path. That means it always takes up the least reluctance path. Reluctance is nothing but resistance in case of electric circuit. As we know that the resistance opposes the flow of current in the electrical circuit, whereas in case of magnetic circuit, the reluctance opposes the creation of flux, opposes the flow of flux. So this is the third point. And the fourth point, it never intersects each other. You can observe the magnetic lines of force in the diagram. It never intersects. You can observe it never intersects. It never intersects. Right? It completes. It is a closed loop. The fifth point, the lines repel each other when they are in parallel. The lines repel each other when they are in parallel. When they come in parallel, it repels and moves in the same direction. The lines repel each other when they are in parallel and moves in the same direction. This is the fifth property of the magnetic lines of force. So here we have understood what is magnetic lines of force, magnetic force, magnetic field, and the properties of magnetic lines of force. Okay. So the next topic for the discussion is the magnetic flux density. You can observe the definition. The magnetic flux density at any point in a magnetic field or the magnetic circuit is defined as the magnetic flux passing through the unit area perpendicular to the magnetic field. So here the magnetic flux density at any point in a magnetic circuit, you can observe this is a magnetic circuit what he has taken. If you observe the diagram, you will come to know this is the magnetic field what he has taken or the magnetic circuit what he has taken. So which is represented by the magnetic lines of force. This red arrow mark you can observe, this is called the magnetic field which has been created at any point. You can consider at any point in this particular area is defined as magnetic flux passing through unit area. Passing through unit area, you can consider, you can observe that green rectangular area. You can observe here what he has taken, this unit area of cross section is considering. Okay, this unit area of cross section is considering or 1 meter square area or 1 square meter area. So in this area, what is the amount of magnetic flux passing? What is the magnetic lines of force passing? This will give you the magnetic flux density in that particular area of the magnetic field. Okay, so which is represented by capital B. You can observe the capital B represents the magnetic flux density. If you observe the formula flux per unit area, the unit of flux is Webers. the unit of area is meter square. Okay, which is also another unit for another alternative name for magnetic flux density is Tesla. Okay, the magnetic flux density, flux per unit area, the unit is Weber per meter square, which is also the another unit which they will call is Tesla. Tesla is the unit of magnetic flux density. Okay, next term, if you observe, it is permeability, which is represented by mu. It is the ability of a magnetic material to conduct or which allows the magnetic lines of force through it. The ability of any magnetic material which allows the magnetic lines of force to pass through it. It is called as permeability. How much magnetic lines of force that the material allows. It is called as permeability, which is represented by mu. Which is represented by mu, which is equal to mu naught. If you observe mu naught, this is called as mu naught into mu r, where mu naught is called absolute permeability or permeability of air or vacuum, whose value is constant, which is equal to 4 pi into 10 raised to minus 7 Henry per meter. The other one is mu r, which is relative permeability, which is equal to 1 for air or vacuum. Again, it depends, the value of mu r, it depends on the magnetic material which is used. If you use iron, the relative permeability is 5000. If you use steel, the relative permeability approximately it is 40,000. If you use nickel, the relative permeability is around 600. If you observe the values of these parameters, that is the relative permeability of different materials, if you observe, we can easily tell which is more magnetic. Here, whatever we have taken in, we have considered iron, steel and nickel, the value of mu r of the steel is 40,000, is around 40,000. We can tell which is more magnetic when compared to other materials. Okay, so by observing the value of mu r, we can easily tell which is the magnetic material which is more magnetic by comparing the values of mu r. Okay. The next topic is the magnetic motive force, magnetomotive force, MMF, which is called as MMF. So here, if you observe the definition, the magnetic force which creates magnetic flux in a magnetic material, the MMF, it is similar to that of EMF in case of electric circuit. Here we are talking about the magnetic circuit. In case of electrical circuit, the MMF is similar to that of EMF. What is EMF? Electromotive force. The force which creates the electrons or the current in an electrical circuit is called as EMF. Similar to that, the force which creates the magnetic flux in the magnetic material is called as MMF. Okay, so almost you can compare the electrical parameters and magnetic circuit parameters. So if you observe the formula, the MMF, which is equal to the product of N into I, where N is the number of turns of coil which is wound on a material, magnetic material, and I is the amount of current which is passing through the magnetic material. Okay, the unit of MMF is ampere turns. The unit of MMF is ampere turns. So the next term is reluctance. Reluctance, which is similar to resistance in case of electrical circuit, which is represented by R. if you observe the definition, the opposition offered by a magnetic material to the creation of flux is called as reluctance. The reluctance is nothing but the opposition for the creation of flux, whereas resistance, it is the opposition for the flow of current. In case of magnetic circuit, it is reluctance which opposes the flow of flux, which opposes the creation of flux. Whereas in case of electrical circuit, it is the resistance which opposes the flow of current. Again, if you observe the formula, the reluctance of the magnetic material is directly proportional to the length of the conductor which is used and the area of cross section of the conductor. Again, you know that you will come across another two parameters which is already known, mu naught and mu r. Mu naught is the permeability, that is absolute permeability, whose value is a constant 4 pi into 10 raised to minus 7 Henry per meter, right? And mu r is the relative permeability of free space or air, whose value is 1 for free space. If you take different materials, the value of mu r gets changes, as already we have seen, discussed. So the next term is electromagnet. The electromagnet is also called as artificial magnet. The electromagnet is also called as artificial magnet. So if you observe the definition, any magnetic material which obtains the magnetic property by providing current, you can observe. Any material which gains or which obtains the magnetic property. The magnetic property is nothing but the force of attraction or the force of repulsion. Any material which has got a force of attraction or the force of repulsion, attraction or repulsion, I can consider that one as magnet. The electromagnet is nothing but artificial magnet. How it can be built? By providing current. By providing current. If you observe the diagram, here you can observe, here he has taken a cardboard, this one which is in the form of solenoid. You can observe this as a solenoid. This is nothing but a cardboard which is in the form of circular fashion, that's all. A cardboard which is in the form of circular form. Okay, ಕಾರ್ಡ್ಬೋರ್ಡ್ ತಗೊಂಡು ಸುತ್ತಿದ್ದಾರೆ, ಕಾರ್ಡ್ಬೋರ್ಡ್ ಸುತ್ತಿರೋದ್ರಿಂದ ಹಂಗೆ ಕಾಣಿಸ್ತಾ ಇದೆ, ರೈಟ್? So based on the cardboard, they have wounded some turns of copper wire. You can observe these are the copper wire which is wound on a cardboard. The ends of the copper wire which has been connected to a key switch in series with a battery, in series with some load, some variable resistance load, ammeter to see the current. It completes the path. Okay, you can observe how to create a artificial magnet or an electromagnet. Any material which gains the magnetic property. How it gains? Here if you pass some amount of current, you can observe, if you provide some voltage, then automatically some current starts flowing through this. Whenever current starts flowing through this, it gains the magnetic property. Here you can observe a dark area around this. Whenever current flows, automatically a magnetic field has been created. You can observe a dark area around this circuit which represents the magnetic field or the strength of the magnetic field. If you increase the amount of current, then automatically the strength of the magnetic field can be increased. The strength of the magnetic material, it depends on the amount of current flowing through this. Increase the flow of current, magnitude of current, therefore you can increase the strength of the magnet. The second point, increase the number of turns which is wound. Increase the number of turns which is wound on the material. Like this also you can increase the strength of the magnetic field. Two ways you can increase the strength. One is by increasing the amount of current. The other one is by increasing the number of turns of coil which is wound on the material. So like this you can build an electromagnet or artificial magnet. Okay. So now you can observe the working principle of DC generator. The first point you can observe, it works on the principle of Faraday's laws of electromagnetic induction or dynamically induced EMF. What does the Faraday's law states? The first law, if you observe, whenever the magnetic flux linked with an electrical circuit changes, an EMF is induced in it. Whenever the flux get changes, whenever the magnetic flux, what is magnetic flux? It is magnetic lines of force. Already we have seen the imaginary magnetic lines of force which is present around a magnet, that is called as magnetic flux. Whenever that flux linked with an electrical circuit changes, whenever the flux changes, an EMF is induced in it. This is the first law. Alternatively, we can tell whenever the conductor cuts the magnetic flux, an EMF is induced in the conductor. Okay. Whenever the conductor cuts the magnetic flux, therefore the flux gets changes, right? An EMF is induced in the conductor. So two ways we can illustrate the first law. Two way, right? The second law, the first law indicates how EMF is induced. Whenever the flux changes, the EMF is induced. That means E is directly proportional to d phi by dt. d phi by dt. E, EMF induced, d phi by dt, the flux subjected to changes. Okay, how EMF is induced? Whenever the flux changes, EMF is induced. Right? The second law, it tells what is the amount of EMF induced. The magnitude of EMF induced is equal to the rate of change of flux linkages, d phi by dt. The magnitude directly depends on the speed of change of flux linkages, the rate of change of flux linkages. It is given by the second law. And what is the direction of EMF induced? The direction of EMF induced is given by the Fleming's right hand rule. So if you observe the Faraday's laws of electromagnetic induction, we will come to know how EMF is induced, the first point. What is the amount of EMF induced, the second point, and what is the direction of EMF induced. Okay, so in order to analyze, let us take up this diagram. That is, here he has taken, already we have seen the solenoid. The solenoid is nothing but a cardboard. Okay, above the cardboard, a copper wire has been insulated. Insulated copper wire has been taken and it is wounded on this in the circular fashion, and which is connected to a galvanometer. Right? Galvanometer show the flow of current and the direction of flow of current. By observing the galvanometer, we will come to know what is the direction of flow of current and what is the magnitude of flow of current. Here he has taken a magnetic field. We have taken magnet means a magnetic field has been created. Here imaginary lines of force is available which is not visible. You can assume imaginary lines of force is present around a magnet. A magnetic field has been created. Right? So now when the magnet is stationary, case 1 what he has taken, when the magnet is stationary means V is equal to 0. What is V? The speed of movement of magnetic field. The speed of movement of magnetic field. Here I am not moving the magnet is stationary. You can observe this is a magnet which is kept stationary. Therefore the magnetic flux of lines does not change. The conductor does not cut the lines because both are stationary. The conductor is also stationary. The magnet is also stationary. There is no movement. Therefore, what is the EMF induced? In case 1, you can consider the galvanometer does not show any deflection, it points at 0. When magnet is stationary, the EMF induced is stationary. When magnet is stationary, the EMF is induced is stationary. We can consider the case 2. When the north pole of the magnet, actually it is, comes nearer to the conductor. You can observe earlier the magnet was in this position. Now you can observe the direction of moment V, which has taken some value. We are moving the magnetic field. The direction you can observe in this particular direction, we at some particular speed. Therefore, the flux lines, it is cut by the conductor. Whenever the magnetic lines of force cuts by the conductor, therefore you can observe the deflection in the galvanometer in the right direction. In the right direction, you can observe the deflection of the galvanometer. It indicates that there is a flow of current in the circuit. There is a EMF is induced. According to Faraday's first law, the EMF is induced in the conductor, which allows the flow of current, in the galvanometer. The direction of current you can observe is clockwise in the right direction. That means in the case 2, whenever the magnetic field is moved towards the conductor at some particular velocity, at some particular speed, therefore the flux lines, it is cut by the conductor, which induces a EMF, which circulates a current in the galvanometer. Right. You can observe case 3. Again, when there is no motion, again I am taking back the magnetic field or the magnet. Therefore, again it is stationary. You can observe there is no deflection. The galvanometer reads 0. Again, case 4, moving away. First, it was stationary. Moving towards the coil, case 2, again stationary. Now I am moving the magnet in this particular case away from the conductor. Moving the magnet or the magnetic field away from the conductor. Now you can observe, again there is a flux cutting. Again there is a change of flux. But in the opposite direction. You can observe the reading of the galvanometer, it is in the opposite direction. That means the magnet is moving away at some particular speed, you can observe. So now, whenever the conductor moves towards, the galvanometer shows the deflection in right side. Whenever the magnet moves away, again there is a flow of current, the magnetic flow, the galvanometer shows the deflection in the opposite direction. Okay, you can analyze like this. So here you can observe when the magnet is moved towards, right, when the magnet is moved away, again in both the cases there is a flow of current. Why there is a flow of current? There is a change in flux, so there is a deflection in the galvanometer. But when it is stationary, there is no deflection in the galvanometer. Here you can observe when the magnet is moved away with greater velocity, if you increase the speed of movement, of the magnetic field, which increases the flow of current, which increases the magnitude of flow of current. Okay. Again, you can consider the case 6. When the polarity of the magnet is reversed, earlier the north pole was coming under the influence of south of the magnetic material, right? Here now, if the polarity of the magnet is reversed, then also the direction of galvanometer is reversed. That means the direction of flow of current get reverses. Okay, like this also you can analyze. So overall, what I can tell, this is the conductor, same diagram. Whenever the direction of movement of magnet is changed, the speed of movement is changed, right? You can observe the deflection in the galvanometer. So now, based on this, we shall move to the next topic, that is the Fleming's left-hand rule. Here you can observe, hold the 3 fingers, that is the forefinger of the left hand, hold the 3 fingers of the left hand, that is the thumb, forefinger and the middle finger mutually perpendicular to each other. If the forefinger points in the direction of magnetic field, you can observe this is a forefinger which points in the direction of magnetic field, right? And middle finger shows the direction of flow of current. If middle finger gives the direction of flow of current, then the thumb will give you the direction of motion of conductor. This Fleming's left hand rule, it is applied for the DC motors. Whenever we will discuss the DC motors, at that time you will come to know. Here just you can understand, if these two fingers, that is the forefinger and the middle finger, you can observe the slide, the forefinger and the middle finger, if the forefinger points in the direction of magnetic field and the middle finger in the direction of current, then the thumb will give you the direction of motion of conduction, motion of conductor. Okay, this law is applied for DC motors. You can observe the right hand rule. This right hand rule actually it is applied for DC generator. First law we have seen how EMF is induced, Faraday's first law. The second law, the magnitude of EMF induced, it depends on rate of change of flux linkages. The third law, that is nothing but the Fleming's right hand rule. In order to, if you want to obtain the direction of EMF induced or the direction of flow of current, you can consider the Fleming's right hand rule. Here you can observe, hold the three fingers of the right hand, that is the forefinger, middle finger and the thumb, mutually perpendicular to each other like this, mutually perpendicular to each other. If the forefinger points in the direction of magnetic field, you can observe forefinger points in the direction of magnetic field, and if the thumb shows the direction of motion of conductor, we were moving the magnetic field, right? You can move the magnetic field or you can move the conductor, right? If forefinger points in the direction of magnetic field and thumb indicates the direction of motion of conductor, then the direction of current is given by the middle finger. Then the middle finger will give you the direction of flow of current in case of DC generators. You can apply this rule for the DC generators. Then the next rule, it is the right hand thumb rule. Right hand thumb rule, you can observe right hand, it states that hold the current carrying conductor in the right hand. Hold the current carrying conductor in the right hand. You can take the right hand, you can hold the current carrying conductor like this. You can observe the diagram. He has taken a current carrying conductor. That means the current is flowing from bottom to top, such that the thumb is pointing in the direction of current. You should hold the thumb in the direction of flow of current. You can observe the current is flowing like this and parallel to the conductor, right? It is parallel, the thumb is parallel to the direction of flow of current. Then the curled fingers, the fingers which has been holded, you can observe the fingers which has been curled, right? These fingers, the four fingers which you can observe, will give you the direction of magnetic field or the direction of magnetic flux. Okay, right hand thumb rule. Hold the current carrying conductor in the right hand such that you can observe the thumb points in the direction of flow of current. Then the curled fingers of the right hand will give you the direction of magnetic flux lines or the direction of magnetic field. Like this you can analyze the magnetic field or the magnetic lines of force. So based on these discussions, let us move to some of the multiple choice questions, MCQs, for the analysis. The first one is the unit of permeance. The unit of permeance. Already we know that the permeability we have seen. It is a property of magnetic material which allows the magnetic flux to pass through it easily. What is permeance? It is a property of magnetic material which allows the flux to pass through that easily. It is called as permeance. You can observe the answers, four answers he has given. In this, The unit of permeance, the ohm, if you observe the option A, it is the unit of resistance. You can observe the ampere, it is the unit of current. You can observe the Henry. Next, the Webers. If you observe the Weber, it is the unit of flux. Then, the unit of permeance you can consider as Henry. The answer is Henry, the option C. Okay. The second question is the relative permeability of air. The relative permeability of air, that is mu r. He is talking about the mu r. Permeability, which is equal to mu naught and mu r. Mu naught is called as absolute permeability, whose value is a constant, which is equal to 4 pi into 10 to the power of minus 7 Henry per meter. Another parameter is mu r, that is relative permeability of magnetic material. But here he has taken the relative permeability of air. Here if you observe the options, here it is the value is 1 you can consider. The relative permeability of air is 1. Okay. The third question is the resistance offered in the magnetic circuit. The resistance offered in the magnetic circuit is nothing but the reluctance. In case of resistance, in case of electrical circuit, we have discussed the resistance. In case of electrical circuit, it opposes the flow of current. Whereas in case of magnetic circuit, it is the reluctance which opposes the creation of flux. Opposes the creation of flux. What is resistance? We know it is a property of my electrical circuit which opposes the flow of current. That is resistance. Right? What is flux? The magnetic lines of force in the magnetic field. It is called as flux, magnetic flux. Therefore, here for this particular question, the answer is the reluctance, option C. The next question, a device which transforms the mechanical energy into electrical energy. The very first question what we have discussed, the very first topic, a device or electrical machine which converts the mechanical energy into electrical energy is called as DC generator or a generator. Motor, reverse, a device which transforms electrical to mechanical, that is motor. Transformers, transfers the electrical energy from one circuit to another circuit, that is transformer. The magnet, magnet is nothing but which exhibits a force of attraction or repulsion, that is magnet. So for this particular question, the answer you can consider as A, that is the generator, which transforms a mechanical energy into electrical energy, that is a generator. So the next question, the voltage can be induced in a wire. How voltage can be induced in a conductor or a wire? According to Faraday's, we have seen whenever a flux linked with the coil changes, an EMF is induced. So he is talking about that. How EMF is induced? How voltage can be induced in a wire? The option A, if you observe moving the wire near the magnet, moving the magnet near the wire, changing the current in a wire, all the above. Here you have to observe carefully. We have seen some of the diagrams. We have taken a magnet and we have taken a conductor. So the magnet we have moved towards the conductor. There was a flux change. In the other way, you can move the conductor near the magnetic field. Then also the flux will get changed. Or by changing the current in a wire, that is statically induced EMF. He is talking about a statically induced EMF in case C. So the option is D. You can consider all the above. By doing all the experiments, you can observe there is a change in flux in the conductor. Therefore, by moving the wire near the magnet, the flux changes. Moving the magnet near the wire, the flux changes. And changing the current in a wire, then also the flux gets changed. Therefore, you can go for option D, that is the voltage can be induced by all the three parameters, by all the three options. That is all the above. So here, the next question is magnetism related to electricity? Is magnetism related to electricity? The option is yes or no. Yes, because by doing all these experiments, what we are getting? We are getting the voltage. We are generating the current. Therefore, the magnetism, yes, it is related to electricity. We can consider. We can consider. The next question is the direction of magnetic lines of force. The direction of magnetic lines of force, you observe the magnet. The direction of magnetic lines of force, it was from north to south around a magnet, and inside the magnet, if you consider, it is complete its path inside the magnet from south to north. So here if you observe the direction of magnetic lines of force, it is from south to north, or second option north to south, from one end of the magnet to another end, or none of the above. Here you can consider it is originates north and move towards the south and complete its path in the surrounding medium, right, and forms a closed path. Here you can take the option as P. It is from north to south. You can consider. The next question, which of the following is not a unit of flux? The unit of flux, actually it is Webers. We know that it is a Weber. The first option is Maxwell. The Maxwell is also a unit of flux. Maxwell is also the unit of flux. It is in case of CGS system. The Weber is the unit of flux in SI system. The Maxwell is the unit of flux in CGS system, centimeter gram system. Okay. But if you observe the option B, that is Tesla, it is the unit of magnetic flux density. Okay. So here what I can consider, it is the option B. That is which of the following is not a unit of flux? That is the Tesla. Tesla is not a unit of flux. It is the unit of magnetic flux density. The unit of flux is Weber in case of SI system, that is Weber. The unit of flux is Maxwell in case of CGS system. So the next question is 1 Tesla is equal to, what is 1 Tesla? What is the value of 1 Tesla? Whether it is 1 Weber per millimeter square, or 1 Weber per meter, or 1 Weber per meter square, or 1 milliweber per meter square. Here you have observed 1 Tesla, it is the unit of magnetic flux density. What is magnetic flux density? It is flux per unit area. In the numerator you are having flux, the unit is Weber. In the denominator you are having area of cross section, the unit of area of cross section is meter square. So based on this discussion, what we can consider, the unit of magnetic flux density is Tesla, and 1 Tesla is equal to 1 Weber per meter square. That is the option C. So you can consider as option C. Okay. The next question is the uniform magnetic field is. The uniform magnetic field is the first option, the field of a set of parallel conductors, or the field of a single conductor, or the field in which all lines of magnetic flux are in parallel and equidistant. None of the above. So if you observe all the four options, easily we can tell, because we have represented the magnetic lines of force, which is all the lines of magnetic flux are in parallel. You can observe the property of magnetic material. You can observe the property of magnetic flux or magnetic lines of force. If you recall, I can tell the magnetic flux never intersects each other. That means they move in parallel and equidistant. Therefore, by recalling the property of magnetic lines of force or magnetic flux, I can tell the option is C. Okay. So, based on these discussions, that is the basic concepts we have discussed on the DC generators, that is the working principle of DC generator. We have discussed some of the topics which is related to the magnetism or electromagnetism, and also we have seen some of the MCQs related to this particular session. By this, let us end up this session. Okay, thank you.